This is Software Engineering Radio, the podcast for professional developers on the web at se-radio.net. SE Radio is brought to you by the IEEE Computer Society and by IEEE Software Magazine. Online at computer.org/software. Collide sends employees important, timely, and relevant security recommendations for their Linux, Mac, and Windows devices right inside Slack. Collide is perfect for organizations that want to move beyond a traditional lockdown model to one where employees are educated about security and device management while they're fixing important problems. Visit collide.com/SERadio to sign up today. That's KOLIDE.com/SERadio. Enter your email when prompted to receive your free Collide gift bundle after trial activation. You can try Collide with all its features on an unlimited number of devices for free for 14 days. No credit card required. Try it out at collide.com/SERadio.
Welcome to Software Engineering Radio. I'm your host, Gavin Henry, and today my guest is Robert Seacord. Robert Seacord is a technical director at NCC Group, where he develops and delivers secure coding training in C and C++ and other languages. Seacord is an expert on the C Standards Committee. His 6 previous books include the CERT C coding standard and secure coding in C and C++. Robert, welcome to Software Engineering Radio. Is there anything I missed in your bio that you'd like to add?
No, that was quite complete. Thanks for having me here.
A pleasure. So I'd like to start off with a brief history of the C language and then touch on why programming in C can be insecure. We're going to also then move on to sort of top 5 security issues, and then the last bit of the show is going to be talking on the various ways and tools we can use to help us write secure C programs.
Okay.
Small disclosure, I might mention an open source project I'm working on called Centripeer, which is written in C for various things that has come up while I've been writing the code, and tools that I found security issues that I thought that weren't an issue, and things that I found in your books, in the sections on how to improve your code. So I think it'll be a nice bit.
Sure.
So let's lay down some foundations. When was C created?
Okay, so I had to look this up because I'm actually not quite that old, but it first appeared in 1972, and it was developed by Dennis Ritchie at Bell Laboratories in New Jersey. Yeah, so it's had a very long history. It was based on a typeless language called B, as you might imagine, because programmers have never been very good at naming things.
Cool. And are there such a thing as versions, or how does that work?
Yeah, well, yeah, there's a lot of variation in what we call C, right? So there was K&R-C, which was Kernighan Ritchie, kind of corresponded to their book back in the 70s. And back in the 70s, ANSI started a committee to standardize the language. So they published their first standard in 1989, so that's often referred to as C89. And the next year, that was published by ISO, so that was fast-tracked to the International Standards Organization, C90. And a lot of people have assured me, including John Benita, who was the previous convener of the C Standards Committee, that those two standards are exactly the same. There's just a different cover page. But it's actually quite hard to find copies of those original standards. But a lot of embedded code is still written to C89, C90. And then there's been several major versions of the standard released since then. So the next one was C99. And C99, was a little kind of slow on adoption, but, added a bunch of features. C11 was the first standard that I worked on from beginning to end. And C11 primarily introduced parallel programming, concurrent programming, threads, thread library, atomics. And it was meant to also address security. I'm not sure it did as good a job of addressing security as it did addressing, parallel execution, but we did add things like Annex K, which is the bound checking interface, or the underbar S functions. Many people think underbar S stands for security, but it actually stands for Balance Controlled Interface. And we added that. We added Annex L, which was the analyzability annex, and made some other small improvements here and there to address security. That was C11.
And that's 2011, isn't it?
Yeah, 2011. We just have the single digits. I mean, I guess eventually we'll wrap around, but I hope to be dead by then and expect it to be someone else's problem.
You mentioned ANSI. That's the American.
Yeah, that's American ANSI. And then nowadays it's
Institute, isn't it?
American National Standards Institute.
Okay, yeah.
But nowadays it's actually, there's a group called Insights, which is sort of under the umbrella of ANSI. And so if you're in the US, you're a member of the Insights committee. And Insights gets a single vote in ISO. So ISO is the international standards body. So it's one nation, one vote at ISO. And the committee's actually, it's very US centric. We had a meeting some years ago in Delft in the Netherlands, and there's a portion of the meeting where we just handle Insights business. So we ask people who aren't part of the US body to leave. And the only person to leave was the host of the meeting. And this was a meeting taking place in Europe. There was only one European there, and it was the host. So usually we get better participation from Northern Europe, Canada, but not much beyond there. Hasn't been a lot of participation from Asia or elsewhere lately.
And is that because C's not used there, or they don't participate?
Well, it might be used there, but it's all the compiler vendors are in the U.S. primarily. There's IBM, their compiler group is in Markham in Canada, and so that's actually the Canadian representation is from IBM, a well-known Canadian company, of course.
And so there's not really versions; it's the standard, and that changes each.
Yeah, well, there's versions of the standard, and that sort of drives the baseline. So, there's C11, there's C17. C17, some people mistakenly call it C18 because it was published by ISO in 2018, but it actually is a 2017 standard. And that was an unusual one. It was just really bug fixes off C11. So no one really should be using C11. C11 is like C17 with bugs, and C17 is C11 without bugs. But there's, of course, all the compiler vendors fix all the bugs in C11, so you won't see them anymore, regardless of which standard you specify. And so C17 is the current version, and we are currently working on C23. And the deadline for papers to introduce new features has come and gone as of this past, I think it was November, as of November. And so we know what's not going to be in C23 right now, which is anything we haven't got a paper on. And what's going to be in it is still up in the air because we have to see if we can get consensus on, the remaining proposals that are in front of the committee.
And that's what ends up in the compiler, doesn't it? What the version or standard the compiler supports.
Well, it could, right?
It could.
So first of all, when we create the standard in C, there's a strong requirement for existing implementations, right? So the C committee, more than most committees, does not like to invent things, so we like to find things that are being used in practice that could benefit from standardization because that might increase portability over a number of platforms, and then, get it into the standard. And sometimes the committee will, I'll use the term, make improvements to the existing practice. They do like to fiddle, and that's good and bad. I mean, it's nice to maybe make some improvements, but at the same time, now it's not exactly existing practice anymore. Right now, you made some changes to it, and some things like Annex K, the committee fiddled with that a bit and got to the point where the existing implementation from Microsoft became non-conforming to the standard, and they weren't really up for changing it. And so, yeah, so the standard, I'm trying to find a different word than standard. It sets a standard.
No, but you touched on a good point there that the standard is there to reinforce portability, I think.
Yeah.
That's what you're trying to get to.
Yeah. But all these compilers, they're always each implementation, right? Each compiler implementation exist over a continuum, right? So you'll have a compiler that has, say, maybe it's fully implemented C99, but they're working towards implementing all the C11 or C17 features, right? And so it's somewhere in between. And then, most compilers have compiler-specific extensions that you can use, right, which are not standardized. And so every implementation, there's a lot of variation. Each sort of standard version is sort of a different flavor of the language, and then the actual compiler implementations, they'll fall into different areas in terms of which standards they implement and which additional features. And so there's a consistent sort of portable, backbone, but there's a certain amount of, variation kind of built on top of that.
Yeah, just touching on the bit where you spoke about it's really C17 and not C18. In my open source project that I mentioned, when I was getting the continuous integration test set up, as it were, to actually build my project with the compiler flags, I put on, it was GCC standard C18 because I'm running Fedora Linux latest for my desktop that I develop on. But the runners where this code was built on GitHub was Ubuntu 20 LTS, and they didn't have that flag support in those GCCs. I think it was there. Or when I was testing on NetBSD and OpenBSD, they didn't. They only supported C11. So even things not even that many years old, they haven't caught up, or it's just the version of compiler that was released with the operating system. So I understand what you mean by depending on how the compilers are implemented and who's rolled them out.
Right. Yeah. And Microsoft is always been an interesting case because they've always been sort of comfortable partially supporting standards. So, supporting parts of standards they like, but ignoring parts they don't. And
but that's not a standard, is it? You either do it all or you don't.
Yeah, that's true. So for a long time, they didn't like all the parts of C99, and they just kind of took a pass on those bits. But they've sort of announced a direction where they want to sort of become more aligned with the C standard. They haven't been sending anyone to the committee meeting, so it's hard to tell, exactly what their future relationship with the language is. But, compilers like Clang and GCC do a very good job kind of keeping up with the latest version of the standards. And you can get some even C23 kind of features supported in those compilers as well.
Excellent. Well, I'm going to move us on to the next section of the show, which is really about the top 5 security issues that I've come up with a bit of research, and I want you to correct me on them. So before we dig into these 5, if we could spend a minute or two to understand why a C program can be insecure, and then we'll dig into the 5 issues that I've listed.
Well, yeah. So all programming languages are insecure, and they're all general purpose programming languages. So they all can sort of achieve the same things, right? So they have the same, they're all Turing complete, right? And they've got different abstractions, different idioms for programming in those languages. But, in the way languages are broken, they can be quite different, right? Because that's not an intentional design. It's sort of the defect surface of the language, or however you want to describe it. And so, if you look at a language like Java, which had been billed as a secure language for many years, it's got some serious problems with things like deserialization, which basically allows an attacker to execute their own code inside your virtual machine, right? So the level of
it's a very topical language at the moment, isn't it? With everything that's been going on the past 2 weeks, we have to be careful of timelines on this type of show. But the big one with Log4j, the poor two open source guys,
right? Yeah, and I mean I haven't studied that carefully. I mean that mostly seems like a design flaw. I mean it's
kind of like you said, where code can be injected and it runs where it shouldn't be.
Right. Yeah. So Java's got a pretty significant attack surface, and it's at a certain level where it's sort of in the libraries and in the features and ways that those features can be sort of misused to exploit the code. C, being sort of a simpler compiled language, doesn't have that attack surface. But C and C++ are sort of well known for memory safety issues. And these are things where basically you read or write outside the bounds of an object. And C and C++, these languages are designed to be optimally efficient. So they sort of trust the programmer is not going to make these type mistakes. And it turns out that trust had been, very misplaced because programmers make these mistakes all the time. And, if you write outside the bounds of an object, that can have various consequences. It's undefined behavior, but, depending on what that write does. And so, it could overwrite data. It could overwrite, function pointers. It could overwrite the return address on the stack. And, attackers can exploit that kind of problem by, among other things, injecting code into your process and overwriting the return address on the stack with the address of that malicious code. So when the function goes return, instead of return to the caller, it executes, code that's been injected by the attacker. And then that code runs with the permissions of the vulnerable process. So that's a pretty significant style of attack.
Okay, well that's a good overview of a few things that being insecure. Let me break down some of them. And before we start on this next bit, when we're talking about C, and you mentioned the word object, which always makes me think of an object-oriented program, like a JavaScript object or a Java one. What do we mean in C when we talk about an object?
Oh, I didn't know this was going to be a really deeply technical.
Well, as simple as you can make it, just to put a single sentence definition on an object.
Yeah, we have a memory management study group that's trying to answer that question. So,
maybe we can't do a simple answer there.
But basically, an object is okay. I mean, so you have in C, you have functions and you have objects, right? So an object is everything that's not a function. So that's a variable would be an object, or you can have an object in dynamically allocated storage. So yeah, it's basically.
That is correct. That is exactly what I was just going to read from your book. So in your book, Effective C, you say an object is storage in which you can represent values. To be precise, an object is defined by the C standard as a region of data storage in the execution environment, the contents of which can represent values. With the added note, when referenced, an object can be interpreted as having a particular type. So yeah, that is a big tick for that answer. Thank you.
Oh, thanks. I'm glad I'm consistent.
So yeah, you touched on a couple of things that I was going to pull apart shortly, and that's to do with how these memory issues are actually exploited. But we'll start off on my list. So doing my own project and other things like that, whenever I save something or I'm working in IDE and I push it to GitHub, I've got all sorts of static analysis on it that we'll mention in the next section, but it usually comes back with something like a string issue. So I've always understood strings to be a security issue, as in not null terminated or an array of characters, people treating that as a string when it's not a string. Could you give us some information on why a string can be insecure?
Yeah, strings are kind of rough, So strings they're not a primitive type in either C or C++. And so they're constructed on top of arrays, and C arrays are problematic in and of themselves, right? And so for starters, we know that there's no implicit bounds checking, and there's a lot of functions, such as stir copy, where you're copying a string from a source to a destination, and it's going to copy the entire length of the string, but there's no indication in that function of the size, say, of the destination array. And so stir copy will just do what you ask it to do, which is copy from this source to this destination without checking to see if there's room for that to make that copy string inside the bounds of that destination object. And so the problem with the arrays, one of the problems with arrays is when you pass them to a function, they decay to a pointer to the first element of the array. And so once you're inside the function, there is no way to determine the size of the entire array. So that size information has to be passed to be available. So functions like stir copy that don't pass the size, the library function is trusting you, the programmer, to pass it an object which will fit into the destination array. And if it doesn't, you'll have this undefined behavior and this potentially vulnerable code.
And so I always remember it that the name of an array is also a pointer. So when you pass it into a function that, like you said, it decays to just a pointer, you can still find out what type of pointer that is inside your function. So is that correct?
Well, I mean, the type of the pointer's typed, So, I mean, you could have void pointers in C, but that's not particularly a great idea. So typically a string would be a char pointer. Correctly, it would be a char pointer. So, yeah, but
so you don't know how long that is, and you have to give
you don't know how long it is, and even the idea that it's an array is not necessarily the case, right? It could just be a pointer to a single character. So
do you have to think about, because what code that I've seen where they pass in the length, they usually lose one of the standard functions, string length. But again, that function has to figure out how long your string is. So do you have to take an extra step and make sure it's got it's null terminated? Or or is there something that we can reach to so we don't have to think about any of this with strings? What do you recommend?
So there's no string type, right? There's no primitive string type. So it's an array. And the definition of a string is that basically there's a null character before the bound, right? So if there is no character before the bound, it's not actually a string. It's a character array, right? And that's okay, right? It's okay to have a character array in C. It's defined behavior, but it becomes undefined behavior if you pass a character array to a strlen function, right? Because it's going to, examine each element of that character array for no character, and it's going to continue looking for no character until it finds one. So if stir length, which again doesn't take a size, it doesn't know what size the string is that it's examining, if it doesn't find a no character before the bound, it's going to continue to look for through memory for a no character. And as soon as that function accesses storage beyond the bound of the array, it's now undefined behavior, right? And once you have undefined behavior in your code, all bets are off, right? That program can now exhibit any type of behavior. So yeah, there's certainly a requirement to ensure that any string you pass to a string function is actually string, meaning that it has a no termination before the bound.
Yeah, I've seen some of the documentation on some of the string functions that look to work around this and they say, if there's not a null character found at that length that you passed in, we'll make sure there's one there, sort of thing.
Right. A lot of functions, newer, sort of more secure functions, will ensure that when they create a string, that it will be properly no terminated. And if you perhaps give it more data than it has room to store in whatever sized object you have, then it will overwrite the last character it's trying to store with a no character. So you've got a properly no terminate string. And so, this choice of a data type was made early on and could very well be the wrong data type. Maybe having a size, followed by the string and not using a no termination, maybe that would have been a better, more efficient, more secure design, but it's not something that's likely to change at this point in the evolution of these languages.
And I think if we move on to number 2 on my list now, I think we've touched a little bit on it, and I've called this buffer overruns and underruns. And I think you've helped me understand a question I was going to ask in this section, where in my project, the CenturyPeer one, I've got some errors on my IDE where I'm doing I think it's a string and compare. So I'm basically checking a URL that comes in to see if it matches to send the data to one of my functions. So I've got the URL, and I've got the size of how long I want to look along the array of chars to find a match, basically. So I've given it a max path length. I think it's of 1024 or something. But my IDE says I shouldn't check that URL string longer than the strings there, even though it finds a match and my tests all work, because I think that's just what you've explained there. Once it gets past the array of chars, which might not be a string, i.e. it's not null terminated, all bets are off because it's undefined behavior when it gets to, say, char 101 of the URL that's 100 chars long type thing.
Right. Yeah, you definitely can't examine characters beyond the bounds of that object, beyond the bounds of that character array.
Yeah, so I think when the URL comes in, you need to do a size check on it and then make sure you're not checking past that for a match. Would be the correct way.
Yeah, so you've got a max path buffer, right, that you're storing it in. So you've got that amount of room for that array, but you're comparing it to, another string, and so, right, you don't want to exceed the bounds of either of those character
it's actually the string and compare. So I've got the URL and the length of the string that I want to compare against. So like /home, I want to make sure that goes to the right place, or about or something like that, about page. And I've got a max length, so it's going along that string for as long as I've passed length for, and it says that's bad. But you don't know how long the path is until you've calculated the path, so you kind of get in this like chicken and egg type situation. But yeah, so when we talk about going past the end of an array, that would be an overrun, is it? A buffer overrun? Or is that an underrun?
Well, yeah. So there's these terms that get kicked around in security, like buffer overflow and buffer underrun and overrun, and I don't know what any of those words mean. They're very kind of loosely used terms in security, but they don't have very precise definitions. So in the C language, really we just talk about an access outside the bounds of an object, and we don't care about what that access looks like, right? So you could start at the beginning of an array, and you can increment, a point or an index, and then, run off the end of the array, right? And that's an out of bounds access. You might call that a buffer overflow. And then, you could start at the end of an array, and you could decrement the pointer, and you can run off that end of the memory. Sometimes you'll just sort of arbitrarily jump from, you might have some sort of integer error and jump from accessing an array to some random place in memory. And again, I don't know what that's called, if that's a buffer overflow or buffer overrun, but it's definitely an access outside the bounds of that object, which is, undefined behavior. You can't take you can take a pointer to an array and you can add or subtract an integer value to it as long as the pointer still refers to the same array or to one past that array, the too far element. But if the pointer you form from that pointer arithmetic is outside of that bound, it's just undefined behavior. And what you call it, kind of varies. There's, it's a little bit unrelated, but people like to talk about integer overflow and integer underflow in C, but there's actually no such thing as integer underflow. That's just someone's creation. If you have an integer operation that forms a value that can't be represented, that's integer overflow. There is no such thing as integer underflow, but people like to use that term for whatever reason.
Well, that's a good explanation. Thank you. So,
Sure.
So we've done something here where we've gone outside the bounds of what we're trying to do. The third thing on my list is what I've called memory leaks. So when you request some memory from the operating system with one of the allocation functions, and you don't free it, so you get what I think is called a runtime leak, or corrupt memory. So runtime would be where you're continually asking for this memory, but you're not freeing it, so you're using more than you should be. Is that a correct definition?
Yeah, so there was a lot of stuff that was slightly wrong in that question.
Good, that's what I wanted to hear. Correct me.
Yeah. So for starters, there's memory allocation function, right? Malloc, calloc, realloc, aligned alloc, right? And none of these directly request memory from the operating system, right? So the process has a memory allocator that runs as part of the same process space, right? And so your memory allocator will request a very large block of memory from the operating system, and then it will manage that. And so when you make a call to malloc, it's allocating, storage. It's allocating a piece of storage from this large block of memory that the memory manager is managing within the process, right? So
is that part of the kernel that's doing this memory management?
No, it's all in your process. So, okay. The memory management, you're going to link to a library, and that library has implementations of strcpy and malloc, and all these functions run as part of your executable, right, in your process.
So this isn't like a memory pool that I've created. This is something to do with how an executable is created.
Well, yeah. So I mean, when you start up, the memory manager is going to go to the operating system. It's going to get a block of memory, right? But then once it gets this large block, which is basically the heap, right? Your memory manager is now going to manage that heap storage for you, right? So when you make a request to malloc, that's going to execute the malloc function, which is part of this, memory manager implementation. And it's going to say, what's the next available number of, next available block of memory that's at least this number of bytes large, and carve that off, this bigger block, and return that to the user. So that entire process doesn't involve the kernel at that point, right? That block's been carved out. The only time the kernel might become involved again is if you completely use all the allocated memory from the operating system. You might then seek to sort of extend that, but that's one implementation. Doesn't necessarily, the other possibility is that at that point the allocation would fail for inadequate memory.
Okay, and so when we're talking about these out of bounds things that happen, I'm not going to use the word overrun or underrun again. Does it make a difference if it's does something out of bounds into memory that we haven't freed, or are we contained within what the memory allocation tool has given us for memory? Or is it just undefined? Is there a difference between, say, we've corrupted some of our own memory or not freed it, and then one of these array operations we're doing ends up trying to go into that? It's just undefined. Or what I'm actually trying to ask is, when you see exploits of these types of things, and they know that we're not cleaning up memory, or there's some type of bit of memory they can get to with this exploit to run their own code.
Yeah.
How do they predictably get at that if these things are all quite undefined and random?
Yeah. Well, undefined, is a term used by the standard, right? So the standard says simply we haven't defined what happens here, right? And so a particular implementation, of course, is going to do something, right? And because it's not defined by the standard what it does, you as a programmer don't really know what it does, right? So sometimes, the implementation sort of aligns with your expectations of programmer of what sort of behavior you're going to get, in which case you could have executables generated from code containing undefined behavior, which is actually correct. But more commonly, if you're invoking undefined behavior, that suggests that you don't have a correct understanding of the language with regards to that behavior, and most likely the code is wrong. Now when we talk about memory, heap memory, there's several classes of potential errors which can lead to vulnerabilities. The first one, which we've kind of discussed already, is buffer overflows, right? So buffer overflows can occur in any memory segment. So they can occur in the stack, in the data segment, or in the heap. And the consequences, so an overflow in the heap, anytime you write outside the bounds of an object, it's undefined behavior.
Can you define the stack and the heap briefly, just in context?
Yeah. So the stack and the heap, I'll start out by saying that neither concept is defined in the C standard. Right? So these are kind of like implementation concepts, but typically a stack is, a data structure which supports program execution by allowing you to, have a function that calls another function, and then, creates a stack frame for a function that it's calling, where it preserves all the local variables and arguments that are being passed to that function and so forth. And then that function could call another function, and that function could recurse, right? So you could wind up with multiple instances of the same function on the stack. And then once the function returns, the stack sort of unwinds, right? So you return back to the calling function and reestablish that function's stack frame so it has access to the local variables. And so the stack is, the execution stack is a data structure to allow for this basically, functional style of programming. So that's a stack. And, a typical variable that you would declare inside of a function, a non-static variable, if you just have a function f and you say int I, that variable is an automatic variable that's declared in the scope of that function. And what happens is when you call that function, a stack frame gets created for that function, and an instance of that variable gets allocated on the stack, right? And so once that function returns, the lifetime of that variable ends, and it can no longer be accessed. So you've got two other data segments. You have the data segment, which is where static variables go, and static variables, global variables are, they have the same lifetime as that of the program, right? So they're always accessible, and that's where you might keep a counter or something, right? Where a function will come, you'll call a function, you'll increment this counter, the function will exit, but the count will still remain because it's a global variable. And global variables have their uses and they have their problems, But the next segment is the heap. And the heap is where dynamically allocated storage exists. And, the heap is, allows you to allocate storage as you need it during program execution. And those objects persist until they're explicitly deallocated or destroyed, right? So those have their own kind of lifetime that's based on you allocating and deallocating. So,
and that's where leaks could happen and memory can get corrupt.
Yeah. So there's the buffer overflows on the heap, and those are exploitable and how they're exploited depends on the implementation of of your memory manager. So some memory managers implement the Knuth algorithm, which uses these boundary tags, where you'll have control structures before and after each allocated block. So if you write beyond the bounds of the allocated object, you'll start overwriting these control structures in the heap, corrupting the heap. And an attacker could overwrite those structures basically, again, to execute arbitrary code. And the specifics of that depend on the implementation of the allocator. But there's also two other classes of problems, at least two other classes of problems with memory, allocated memory. So one is you allocate memory and then you fail to deallocate, to release it. That's a memory leak. And, a memory leak can be benign if you have a short running program and you don't ever exhaust memory. But if you have something like a server that's going to run for extended period of time, as it runs, if it's continually leaking memory, that memory is no longer available to the memory allocator to allocate to the process. So eventually that system is going to exhaust memory. And that type of defect, once that happens, your server's not going to be very effective at serving, because it's going to start having memory failures and constantly be in a state of trying to recover from memory errors. And so that situation is sort of known as, resource exhaustion. And one form of attack is, denial of service, attack by resource exhaustion, right? Where an attacker, finds a memory leak in your system, exploits that to exhaust your memory. And now it appears that your server is operational, but actually it's no longer serving requests because it's out of memory and it can't function properly. Right? So out of memory, failing to properly deallocate storage when it's no longer required can lead to those sort of denial of service attacks. The other problem is you can accidentally release the same storage multiple times, right? And that's often referred to as a double free vulnerability. Double free vulnerability it looks a little bit different, but it can have the same consequence as a buffer overflow in a heap, which is that an attacker could exploit that to execute arbitrary code. So double free is also quite dangerous sort of coding error.
Would you be able to give an example of, I know it's hard because it depends on the program and implementation of where it's running and things, as far as I understand it, but how can an attacker exploit what you've just explained with a double free or an overrun or underrun? How do they get this code? Is it assembly language that they put in the code and they inject that into this memory of area of memory, or what does that look like?
Yeah, well, so if we just discuss just sort of a basic exploit,
like print in your name or something, I don't know, something really easy to get our heads around.
Yeah, independent of the error rate. I mean, so what can happen is an attacker can inject executable instructions into your process memory, and it can really do that on any input operation. And there's valid, there's executable code that looks like valid ASCII. There's executable code that looks like valid, UTF-8 strings. So, whatever type of string you're inputting, it's always a good idea to validate that string to the extent possible, but sometimes you just can't. Sometimes it's just kind of, a string data, right? And so
I think you've got a really good section in your Effective C book on validating the program arguments. on the command
Yeah,
line.
yeah.
I thought that was
And
pretty extensive.
oh, thanks. And I mean, secure coding in C and C++ really goes into these exploits more. The effective C book is meant more of a introductory text, so I don't try to go too into depth in how exploits or how to write exploits, but I try to write that book to provide kind of a strong foundation to programmers. So
I think that's why I like it so much.
yeah, well, thank you. I mean, in a way, if you code correctly and you avoid undefined behaviors, right? Your code is secure. You don't need to understand how it might be exploited. The study of sort of how code is exploited is really motivational, right? It's for people like, oh, I've got legacy code base with tens of thousands of errors, right? So how do I prioritize that? And so, you kind of talk about what the various errors are, how they can be exploited, how you might mitigate against these problems with sometimes sort of runtime strategies, which would protect against exploits of all of these, and then also about secure coding practices, how to correct the code so it's not exploitable. But getting a legacy system, poorly written legacy system, to be secure, can be a significant investment in rewriting and improving the code.
Yeah, I think you've touched nicely onto number 4, which is on my list, which is inputs. So I've got some questions to do with processing command line arguments, environmental variables, defensive programming, how network traffic is processed at runtime into data structures, things like that. But I think just really understanding, listening to what you've explained with the memory leaks and attack vectors, it just depends on how the input is coming into your program and that you process it correctly. That could be how it's, when you see the CVE exploit list and it says, there's a double free or a buffer overflow or something, in certain situations doing this, if the wind's blowing northwest and you're wearing your favorite jumper, this might get exploited type thing. It just depends on how it's coming into that program and what the program does. Is that a fair summary?
Yeah, it's, some of it's quite tricky, right? I mean, so you'll look at some source code and it will have, have some undefined behavior, and it might be, on this platform under these circumstances with whatever runtime protections are available, that this particular coding error won't be exploitable, right? But you could run that you could port that to a different system. You could run it on a different platform. You could change something about the runtime environment, or, you could upgrade your compiler where the compilers now, used to do one thing with an undefined behavior, but now they've developed an optimization that takes advantage of that undefined behavior to improve your performance. And now, a problem which was, the error was always present in the source code, but now because of this new optimization, that executable has been changed, and it's now, now is vulnerable to attack. So sometimes, many times it's easier to repair the code than it is to understand all the potential security consequences of an exploit. So some cases where it's cheap to fix, it usually just makes sense to fix it. I mean, there's some cases where, if you put some code on the Mars rover and you landed on Mars, right? It's a bit more involved to repair that code, right? So you want to analyze that defect more. You want to analyze that vulnerability more to find out whether it's, how much of a security risk is it worth repairing or not. But in many cases, it's just easier to make the repair to the source code, because if the undefined behavior is eliminated, you shouldn't have a vulnerability in most cases. Now there are vulnerabilities which can exist absent of undefined behavior. These can be logical errors, or just simply things like a memory leak, right? So if your program accidentally, prints out or logs, some personally identifiable information, it doesn't necessarily have to have undefined behavior to do that, right? So you could have a I almost want to use the phrase insecure by design, right? Where there's
which has nothing to do with C. That's just the software engineering has not thought about that.
Right.
Okay, I think that was a good summary. And so with say an improved compiler, could that catch a double free if it's tracking the amount of times you freed something, or is that what a garbage collection system would do?
Oh, yeah. Well, C doesn't really have garbage collection, so
yeah, no, that was just an example.
Yeah. So double free, those type of errors, there are ways to catch it, right? So one mechanism is just to so a compiler does some analysis, right? It doesn't do a lot of analysis. So there are static analysis tools that do more in-depth analysis.
Yeah, that's what I'm going to touch on in the next section.
Yeah.
I've really enjoyed this middle section, so I better move us on because we're a little bit over our time on this bit. So just the last thing I have in my list, because I think we've done a really good job, and I didn't say at the time, but I really enjoyed their description of the stack and the heap. That made everything really clear.
Cool.
So my last point is, sorry, that was a bad pun, is dangling pointers. What are these and what problems do they cause? Just a minute or two, and then we'll move on to the tools to help you be a better programmer.
Well, they certainly cause bad puns, but the problem with a dangling pointer is that it could lead kind of directly to two classes of exploitable defects, right? One being double free, which we've just discussed, right? So if you free a pointer and you don't assign it to null, you could free that pointer second time, and we've already discussed that can be vulnerable. If you do set it to null and you free a no pointer, that's a no op, so that has no effect on the code. The other problem with a dangling pointer is that it's now pointing to memory which has been deallocated, possibly deallocated, and then reallocated. So writing to that pointer is now undefined behavior. And say that storage is deallocated, you write to it. Once you deallocate storage, the memory manager takes it over, and it might use the kind of user space to insert control structures in order to keep track of free blocks of storage. So if you write to these dangling pointers, again, you could overwrite these control structures, corrupting the heap and potentially doing that in a way which, again, makes it possible to execute arbitrary code.
Yeah, I've seen that in a lot, and something that I do in my code. And in Jens Gudstad's book, who I had on the show, and who you know because you work with him in standards, episode 414, and also a shout out to your article for the IEEE secure coding in C and C++, and strings and integers, and your other article on effective C. And I've got those links in the show notes. And all his, and I think in your code examples, after a free, the pointer is set to 0, which is the null alias as well. Excellent. So that was a really good coverage. So in the last section, I don't have as much time as I hoped, but we've done a good job and some crossovers here. So we've got IDEs and things that we use as we're writing the code that try and give us as much help as possible. We've got our sort of build tools, but you mentioned earlier static and dynamic analysis. I think you mentioned dynamic analysis, but I'll mention it here anyway. So what's static and dynamic analysis, and how do they help?
Yeah, so these are just kind of tools and approaches to analyze the code and understand what it does and what potential defects it might have.
So that looks at the source code, the physical files. Well, not physical, the text files, as it were.
Yeah. So static code analysis. I mean, it looks a bit like a compiler, right? So it builds your source code and builds typically an abstract syntax tree. So it creates a structure, and then it might build some additional graphs that can be analyzed. And Then you'll have a series of rules where you'll say, I don't want to free a pointer and then free a pointer a second time. And so, the static analysis will, examine the graphs of the source code, the abstract syntax tree, and it will look for, different structural, various structural defects in the code, or potentially do some path analysis or some data flow analysis. So static analysis tends to be very good at finding, say, structural problems in a program. It's not as good at data flow and control flow type of things.
No, the things that it caught me on is where you return from a function because there's an error, but you haven't freed what you've allocated beforehand. And that's always something that I find on my stuff.
Yeah, I mean, there's some problems that are fairly amenable to static analysis, but frequently, memory management, concurrency, these aren't always discoverable through static analysis. So often, dynamic analysis is more effective to find these type of problems. And so you do have things like address sanitizer and thread sanitizer that are available in Clang and GCC, and these let you and a variety of other products, but these allow you to instrument the executable, and then once it's instrumented, you'll exercise it using whatever variety of tests you have available, perhaps using fuzzers to drive the code with various inputs. And these instrumented executables now will be able to basically trap on any sort of violation. So they're very dynamic analysis is more effective at discovering things like dynamic memory issues and concurrency issues.
Yeah, some of the stuff
basically at runtime.
Some of the things that you've mentioned in your book that I've played with and that I use in my project is the sanitizer ones, the TSAM, which is the thread one, the ASAM, which you mentioned as well, the address sanitizer for memory things, and then the UBSAM, which is the undefined behavior. And where I seem to find errors using those is when I'm running my test suite, because I'm not as careful as when I'm actually running the core product, as it were. I always find issues where I've set up the test case, but I haven't torn it down right or something, which is kind of a biggie, and you should sort it out, but at least it finds them. And then some of the other tools that I see other people use is the sanitizers, the Clang sanitizer one that you mentioned, and then there's loads of, I think it's a lot, you mentioned a few in your book, but if you've got an open source project, it's quite easy to get access to all these free tools, but I think most of them are commercial. And I'll put some links into my show notes for that.
Yeah, and I don't know where to go with this. I mean, it really, C is a difficult language. I mean, and C++
it's simple, but it's simply hard as well, isn't it?
Yeah, simple. I'm not sure, yeah, it's smaller than other languages, and so I guess from that respect, you could say it's simple, but there are there's so many layers to it, that I'm still peeling after. Say I started programming C in 1985, so still peeling after.
And what sort of things have you come up with recently that have surprised you?
Oh, so here's a good one. This was probably the most recent thing that surprised me. So you can define an enum, and you can have an enumeration constant, which has a type, which is different from the base type of the enumeration type.
Yeah, because I thought enums were just supposed to be a thing that meant something to you.
Yeah. Well, there's this question. There's always this question of, what is the type of these things, right? So you write enum, color, red, green, blue. Okay, so what?
Yeah, the normal example.
Yeah. So what type are those things, right? So there's a strong tendency to, well, the standard will say, that the enumeration constants, the red, green, blue, those should all be int. But you could say, for example, you could pass your, GCC or Clang, flag which says use short enumeration constants. So in a case like that, red, green, blue, GCC or Clang might say, well, I've only got 3 values, 0, 1, 2. I can easily fit that in unsigned char. So I'm going to save quite a lot of storage and make this an unsigned char. So now you've got the base type of this object is unsigned char, but the type of each enumeration constant is int. So, and mostly you don't notice this, but there are cases where, say you're doing generic programming and you're trying to, execute some particular code based on the type of something. It might come as a surprise to people to discover that the type of the constant is different than the type of the enum object, right? That's somewhat surprising.
Yeah, that's a good one.
Yeah, that's the one that's got me most recently. But
you mentioned something there that what's the point of a signed char and an unsigned char? Just because you mentioned it.
Yeah, well, signed char and unsigned char are basically small integer types.
Okay.
If you want to represent a character, you should use char, plain char, and all 3 of those types are different and incompatible types.
Perfect. Okay, just before we start wrapping up the show, just to put some more meat into the tool section. So we had a good cover of static and dynamic analysis. We've mentioned the TSAN, ASAN, and UBSAN, sorry.
UBSAN, I like that.
Yeah, UBSAN. Fuzzing, which is a good one. But over the show, we spoke about Annex K. Is that something that we can actually use today? It's been out for a while. You mentioned it in your book, and Jens mentions it in his.
Yeah.
Do you recommend it?
Yeah, I like it. There are 2 schools of thoughts there. And we voted on this in committee a couple times, and the committee's equally divided on this. Half the committee hates it, half the committee likes it, right? And because it's in the standard, you can't eliminate it. You can't change the standard without consensus, right? It's the status quo unless, you can't add anything, you can't remove anything without consensus. And so, some of the history of this, it started with Microsoft back in the 90s, as a reaction to some, well-publicized vulnerabilities. And, basically it sort of improves upon the existing string library functions by typically adding an additional argument which specifies the size of the destination array. Right? So now when you call these functions, they can determine that, there's not enough room in this destination array to make a copy of this string. And so rather than right beyond the bounds of the object, I'm just going to, indicate an error either by invoking a runtime constraint handler or returning an error value. And so I like these. I think they improve. They make it easier for novice programmers to avoid buffer overflows, undefined behaviors. Companies like Cisco have used these extensively and have, swear by them. They claim to have had, significant improvement in quality and security as a result of using these functions. So they're available. Clang and GCC, a lot of vendors sort of don't like these libraries. That might be because they originated from Microsoft, or it could be other reasons. But there are third-party versions of these libraries that you can download and use, and they are standard APIs. So I like them. I would recommend their use.
Thank you. And there, to finish off this section, there's standards that we talk about. There's the CERT guidelines, the MISRA C. Yeah, that's right. I remember listening to a show about SQLite, how they spent a year getting their C code up to some medical standard. I can't remember what it was, but I'll add it in. Is that a thing? Is that something you've heard of? Some type of medical
standard? No.
Some type of medical standard where that code is suitable to be deployed in medical equipment. I'll have to do some more research for that bit.
Yeah.
Okay, so I think that was really good. So let's start wrapping up. So obviously C is a very powerful language with a strong history and deployment base. But if there was one thing a software engineer should remember from our show, what would you like that to be? If we haven't covered it, or just something you want to bring to the top.
Yeah, okay. I'll say this. Yeah, so we didn't spend a lot of time talking about IDEs, right? But there's an interesting thing people will say about C programmers is that C programmers are a little frustrated by sort of compiler diagnostics, and they want to get past that so they can get to the real job of debugging the program, right? And there's one style of programming which is this trial and error, right? So you have a bit of a problem, you Google, you go to Stack Overflow, you find a code example, you copy paste that into your system, you tweak it, you compile it, it doesn't compile, there's some diagnostics, I misnamed this variable, misspelled, you make some improvements, it compiles, and then you run it and it doesn't quite run, so you change something and now you get a run that succeeds and you're like, cool, that's working, on to the next thing. And so this kind of technique of trial and error, it can get to a program which works in a kind of a optimal scenario, right? But it doesn't mean that program's correct, right? You don't know how that program's going to deal with kind of unexpected data, and we talked about input validation briefly, but really your code has to work with all possible data values, right? There can't be any inputs for which the program's going to exhibit incorrect behavior, right? So that's the point of input validation and programming in general, right? Make sure that you deal with all possible combinations of data. So to do this, trial and error is really insufficient. You need to understand the language, you need to understand the code you're writing, and make sure you understand all possible cases, that you're considering type conversions, you're considering integer overflow, and all these
an IDE,
possibilities.
I switched to one. I used to just use text editor, I think, and whatever you use, and there's loads of C plugins, and the amount of time you save by just looking at what gets highlighted, or before you've even clicked build, or you've run a make command, most of your problems are solved if you just pay attention to the IDE.
Yeah, it helps a lot, but it's still definitely inadequate, because all of the tooling isn't going to find all the problems. So it is helpful to to understand the language you're using, and you could achieve that through training classes. You can achieve that through reading. One thing I did when I sort of transitioned from being a programmer to a secure coder is I spent some time mostly in Visual Studio, and I'd write a little bit of C source code, and I would sort of predict in my head what sort of assembly would be generated from that code, and then I would compile it, and then I would be surprised. So I would go back and read the standard, like, okay, now I understand. And so eventually I got to the point where I could successfully predict the assembly code that's being generated. Until you get to that point, your understanding of the language is sort of falling short, right? So
yeah, there's something to be said for just actually experimenting and I like to call it proving it to yourself, basically.
Right.
Have that assumption and write a test or something.
Yeah, and you what I do is I kind of perfect some code, right, where I gain a lot of confidence. I understand this. I know what this is. I can use this, and now I've got kind of a reusable component I can use. But it's quite dangerous to sort of just throw in a bunch of things because they're there without really understanding it yet. So I mean, maybe it's more fun, but it doesn't necessarily produce secure systems.
So just to summarize before we shut up the podcast, what one thing would you like them to remember? Is that be good with your IDE, pick a good one, or prove your assumptions, or what would you like them to remember out of that?
I would say the best time to avoid a defect is when you're coding. So it's better to write correct code initially than it is to try to find and repair defects downstream. I mean, correct coding, quality code, secure code, it's difficult to achieve, and you really need to use all the available tools and processes and discipline to get close to achieving that. But yeah, the most important thing is sort of writing code securely to begin with.
Thank you. If people want to find out more and explore some of these things we've chatted about, where's the best place to get in touch? You're pretty active on Twitter. Is that the best way?
Yeah, I can be found on Twitter. I have a website, robertseacord.com, I think, where I've got some errata for the Effective C book. There's a link there.
I think you need to update your SSL certificate, because I was looking at that last week.
Yeah,
and it was complaining.
Oh yeah,
that it was insecure of all things.
Yeah.
Okay, so your Twitter account and your Robert.
Yeah, you could look there. I'm on LinkedIn as well, so I'm not very hard to find. I don't have any handles anywhere. I guess I'm.
Yeah, it's our RCS on Twitter, for those that want to go there straight away. Okay, Robert, thank you for coming on the show. It's been a real pleasure. This is Gavin Henry for Software Engineering Radio, and thank you for listening.
Thanks for listening to SE Radio, an educational program brought to you by IEEE Software Magazine. For more about the podcast, including other episodes, visit our website at se-radio.net. To provide feedback, you can comment on each episode on the website or reach us on LinkedIn, Facebook, Twitter, or through our Slack channel at seradio.slack.com. You can also email us at team@se-radio.net. This and all other episodes of SE Radio is licensed under Creative Commons License 2.5. Thanks for listening.